All right, this video is going to cover our second special case for the Routh tables and the Routh-Hurwitz criterion. So let's look into this case where we actually have an entire row of zeros, not just zero in our first column. This is caused by an even polynomial that is a factor of the original polynomial, just as some background information. But what this really means is that we have one of three potential cases. And so to explain these cases, let's draw our real and imaginary axes here. And so our first case, we have real poles that are symmetric about the origin, right? So one is real or one is positive, one is negative. They are both real here, right? We'd have an unstable system in this case. Our second case is that we have imaginary poles symmetric about the origin. So this is B here, right, where it's now marginally stable looking. And then for C, we have complex poles, and there are four of them, one in each quadrant for this system. So we'd end up with an unstable system in this case as well here, right? So how do we determine which case we're dealing with? Or maybe multiple of these at the same time. Let's say we have a fifth order polynomial for our denominator for some transfer function. Let's build our Routh table. And let's just say that our third row ends up being a bunch of zeros. What are the steps that we need to take to determine whether we have a marginally stable system or an unstable system in this case? So the first thing that we're going to do is find the row of all zeros, right? That's obviously our third one right here. And then we're going to go to the row that's above that, this s to the fourth, where we have a4, a2, and a naught. We're going to get a new polynomial using the coefficients of that row above. So since it starts with s to the fourth, we're going to have this even polynomial, p of s, a4, s to the 4, right? Those two go together. We skip s to the third, we go a2, s squared, and then a naught in this case. So we're taking the row above it, whatever value it starts out with, s to the fourth, s to the sixth, for example, that's the first polynomial term, and then we go every other one, right? After we do that, we're going to get the derivative of this with respect to s, right? Which in this case is 4a4 s cubed plus 2a2s plus 0, right? Now that we have this polynomial, take its coefficients and replace this row of zeros with that. So the 4a4 is going to replace that first zero in the first column. The 2a2 is going to replace that second zero, and the third zero is actually still going to be a 0 in this case. Step number 5 is we're going to just build our table as normal from there, as we always would, and fill out all the other entries. But then now, our final step, step number 6, is to do analysis of the table, right, with the special case. So we break it up into two parts. We look at before we replace that row of zeros and after we replace that row of zeros. So before we replace the zeros, the number of sign changes tells us the number of right half plane poles up to that point, right? So if we're unstable up to that point. After that, once we start at the row we replaced all the zeros on, right, the number of sign changes equals the number of right half plane poles, which also equals the number of left half plane poles, because all those ones with right half plane poles before were symmetric, right? That's due to that symmetry factor, right? The number of imaginary poles is equal to the order of that p of s, right? That even polynomial, minus 2 times the number of sign changes, essentially subtracting all those other poles that we had just from that previous criteria right there. So let's go through an example for this. Let's say we're dealing with a fifth order polynomial here, or a fifth order transfer function. Let's build our table as we normally would. We're going to have 6 rows. We're going to have 3 columns here, and we can fill it out as normal. And we actually end up with, in this case, s cubed, that row being all zeros. So we recognize that is our row of zeros, right? We find p of s, so we go to the row above it. That is s to the fourth, right? So we're going to have that first coefficient, 7, multiplied by s to the fourth. Our second coefficient is going to be s to the second multiplied by 42 is the coefficient itself. And then the last thing is 56 times s to the 0 in that case, right? We take a derivative of that, and those coefficients are going to be the ones that replace this row of zeros, right? That's step number 4 here. So now we have 28, 84, and 0. We move forward as we normally would and crunch all the numbers for all these different things, right? And then we do our analysis. if we analyze rows 1 to 2, before we replaced our row of zeros, right, we have no sign changes, which means we have no right half plane poles. We need to have one left half plane pole then for the change from row 1 to 2. We had no sign changes, so that's one left half plane pole. Then we look at rows 3 on, we had no sign changes, so no right half plane poles, right, which means that the number of imaginary poles is just going to be essentially all the other ones that we have left over here, right? So we had one that was in the left half plane, and then the rest are going to be our imaginary based off of that other criteria here, right? And I just want to present here, we're not going to go through it in detail, but I encourage you to actually review this on your own and try and crunch it out and come to me if you have any questions. Let's say we have an 8th order polynomial here, and we had a row of zeros around that s cubed part. Which means we have 5 rows before that, right? We can go through all the same exact steps, right? But what I want to show here is that from rows 7 to 6 and then 6 to 5, we have 2 sign changes. So before we even had that row of zeros, we had 2 right half plane poles. And then after the row of zeros, there's no sign changes. That means they're all imaginary poles from there. So that's 4 imaginary poles based off of that math. This was 8th order, so the last 2 poles have to be left half plane. They have to, right? So we ended up with 2 right half plane, 4 imaginary, and then 8 minus 4 minus 2. We had 2 poles left over. They have to be in the left half plane. All right, and that covers our second special case for Routh-Hurwitz tables.